been infected? Well, in the case of modifying the actual syscall entry tables, yes, there is. We can compare it to the original syscall entry table in the mark binary. If we, for instance, use, we can use NM or we can use utool, whichever suits you the best, to look up the syscall entry table. And in this case, so this example is a bit complex, but we know that the number of syscall entries is difficult. 427, which in hex is 0x1AB. Then we can search for this value in the kernel using the utool, which basically just outputs in a decimal. And then we can grep for this value. And as you've seen in this example, we found it here. And guess what? 32 bytes later is the syscall entry table. So we can read the kernel into a buffer. We can find the sys entry table using the nsysm symbol, and we can compare to the original content of the drive. So here's this really nice function that reads in the kernel and actually searches does a binary search, finds the nsysm table, the nsysm variable, and then the sys entry table in order for us to use that as a reference. And since we're running all of this in user space, it's really simple. So we have this function that reads up the mark kernel from disk. Then we can just do task for PID, open up the memory for the kernel, and just read using vmread and compare these tables to make sure that they're actually the same. There are, of course, other ways of subverting syscall functions than to actually change the sys entry tables. But if we have a rootkit that actually does change the sys entry table, and this could be changed using either the kernel extensions or this method, the method of actually finding or detecting the change is the same. So we can do these searches from user space very simply using these tools. I can mention that other types or other ways of subverting a syscall would to be, for instance, to go into the all right, let's try again. All right, now you can hear me. Yeah, so a different way of actually subverting the flow of a syscall is to use is to subvert the interrupt handler. So whenever a function or a user function wants to invoke a kernel syscall, it actually goes through the interrupt handler and the interrupt handler table. So we can actually modify or change that as well. But the interesting thing here is that the method of actually opening the kernel from hard drive and comparing it to the actual kernel in memory is valid even in that case, because we can do the same thing. We can compare what we are expecting on disk to what we are expecting to see in memory, and it applies to basically all kernel functions or kernel methods that are static. Of course, it doesn't apply to something that is dynamically allocated, but for basically everything else that might be interesting, it virtually applies. I'm sorry I can't run a demo here, but I can mention a few other ways of doing basically the same thing. If we want to detect that someone has subverted something in the kernel, we can look for artifacts of that change that has appeared. For instance, we could compare the number of open sockets that the system has available to the list of sockets that we are actually able to bind. So if a backdoor has binded the port 999 and it has been hidden, we could try to bind all of these ports And when we run into a port that is not listed, but that we are unable to bind, that would be the indication that there is something wrong. So, if you want to delve into this deeper, there's a number of really interesting sources out there. We actually have abusing Mark on Mac OS X by Nemo. It's what actually the thing that got me interested in this topic. We have Mac OS X Wars, X New Hope of also by Nemo in FRAC64, and of course we have me and Bosse's article in the latest FRAC 66. There's the Mac Hacker's Handbook, and also the slides and some of the code should be available on the website. Unfortunately, the website is currently down. Otherwise, I might have been able to run the demos. Sorry. But I'm sure as soon as Bosse gets better, he will be able to provide you with the demo code as well. And we would like to thank Hack.se, Rebel, Nemo, and the people at Basic, and of course the people at Cybercom for making this possible. That's it. Do you have any questions? I see someone has a question. Thanks.
Hi, thanks. I just wanted to ask, do you know how much of this is relevant to the iPhone as well?
It's relevant to... interesting question. How much of this is actually relevant to the iPhone? I would say almost all of it is relevant to the iPhone. The iPhone has a few peculiar features with regards to signed binaries and stuff like that, which might make things a little bit difficult. But once you actually root and you start to write into kernel memory, most of these things are basically gone. But you would actually have to do it, my guess is, on a jailbroken phone. But it should be applicable if we disregard the things about the signed binaries. More questions?
Hi, my name is Michi Leenaas from NLS Foundation. So I came here because I thought you'd be doing something similar to a project that we fund called Ksplice that does real-time kernel updates, but to patch kernel holes. Have you ever tried patching kernel holes that you found in so to see if you could use this in a benevolent way?
So the question was basically, is there any good ways to use this technology, or can you use it for good? And the answer, of course, yes. If you, for instance, find a security hole in one of in a kernel function. The example that I have for you is for the Linux kernel. I believe it was membreak or something like that, which was a kernel function that had a serious fault in it. I used a Linux kernel module to just hook that function, do the sanity checking on it, and that's just pass the control back to the original function. And of course, you can do this in Mac OS X as well, using both kernel extensions and these memory patching techniques.